everyone, this is Joel Smith with the ASQ Stat Division, and I'd like to welcome you to today's webinar. Our topic for the day is Design for Variation, which will be presented by Jaime Glanovsky with Pratt Whitney. She's been there for about 5 years in the Design for Variation group, which encourages statistical thinking and tool use among engineers, and recently became discipline chief for the new Design for Variation group at Pratt Whitney. So I would like to go ahead and thank right off the bat Jaime for presenting today. She presented this topic at the Fall Technical Conference. I can vouch that it was popular enough that people were literally standing in the hallway outside of the room to try to listen. So I'm very excited to have her here today. Just so everyone knows, your phones are muted. If you have any questions for the speaker, you can go ahead and use the chat dialogue in the GoToWebinar interface. If it's something that maybe is a clarifying point, we'll go ahead and ask as we go. Otherwise, we'll hold larger questions until the end of the presentation. So I'll go ahead and turn things over to you now, Jaime, and we'll talk again at the end here.
All right. Thanks, Joel. And good afternoon, everyone. Thank you for joining us. So today I'd like to present to you a discussion on design for variation. It's our own personal statistic engineering initiative. Now, my name, as Joel said, is Jaime Glanovsky, and I previously worked in the statistics group at Pratt Whitney, though as he said, my job has recently changed. All right. Before we get started, let me give you a real quick background on Pratt Whitney, where I come from. We're an aerospace company with about 100 years experience in designing, making, and producing jet engines. You can see our products anywhere from the commercial engines on the aircraft that you fly on any given vacation week, the engines used in military fighter jets, and then products as varied as the small turboprop engines that you see on regional jets or on personal aircraft, up to the extremely large turbine systems that are used as power generators. So here's an outline for the discussion today. I'm going to start off with a brief introduction of what statistical engineering is, but I'm not going to go into terribly deep depth about it. Then I want to talk about the pull for statistical engineering, specifically relative to Pratt & Whitney. We had a lot of pull for this before we ever started doing anything. We had quality initiatives paving the way for us, and we had vice presidents challenging us to do more and more, where statistics just seemed to fit right in and give us the answer for how to do it. Then I want to go through the keys to success. What we learned in doing our statistical engineering project were the most important things to have in order to succeed. I'm going to go through some of those keys, and I also want to cover with you a few brief success stories, what DFV has done for us, and wrap up the talk today with some advice for how you could bring similar statistical engineering initiatives into your own organization, whether you're from a very large company or a very small one. So statistical engineering. Now, Roger Hurrell and Ronald Snee, back in 2010, wrote a very popular paper on defining statistical engineering and arguing for where it could be useful out in the commercial world. But the term has actually existed for a lot longer than that. It was just never so well defined. The real reason it's becoming so popular now is because it's one of these ideas whose time has really come. Hurrell and Snee described statistical engineering as the link between those of us that think statistically, statisticians that think in terms of probability distributions and confidence intervals, and those out there actually using statistical methods and tools, but who may not have all the training to think the way we do. Of course, my company was one perfect example of that. We had a small group of statisticians who think in terms of probability distributions and confidence intervals, and then we had a much, much larger group of engineers who were given some basic introductions to statistics. They had access to softwares like Minitab and SAS and JMP, but they didn't necessarily have all the same background, all the ability to think in terms of statistics. They were thinking in terms of durabilities, stresses, and lives. So the first thing I need to emphasize when I'm telling this story is that this is not something that happened overnight. It didn't happen in a week. It didn't happen in a year. It took a long time for us to get from the very humble beginnings of this quality initiative to where we are today. To start out with, back in 1996, Pratt & Whitney introduced its ACE operating system. And it was just our own personal quality initiative, the way a lot of companies have used DMAIC Six Sigma. The important thing about ACE for us was that it encouraged all engineers to have at least a very basic introduction to statistics. As part of their ACE training, they took some courses that covered the ideas of confidence intervals and probability distributions and regression modeling. They were at least made familiar with the concepts and the power those concepts had to help them solve problems. And actually, we were lucky enough that some of our engineers really took the lessons to heart and trained themselves up to be more proficient in beyond basic statistics. Because of ACE, statistics really became a common idea across Pratt. We didn't have to start by introducing everybody to what it was to begin with. So after about 5 years of slowly working the ACE operating system into our company, we adopted lean principles into it as well. And that changed a bit of the focus so that now, in addition to quality, ACE was concerned with how can we reduce cost and waste of time. And of course, the big lesson that came out of that was the earlier you can catch a problem with a design or a product, the earlier in the design phase you catch it, the more money and time you save yourself. Obviously, the later and later you catch it, the more work you have to do to undo what has been done. After all those years, we're feeling pretty good about ourselves, the improvements we made as a company, the advances we made, the problems we'd stopped or prevented. So in 2003, our parent company, United Technology Corporation, or UTC, came in with a technical advisory committee, third-party committee that was going to evaluate what we do here in engineering and come back with any recommendations of areas for improvement. And when they did come back, they had one resounding item for us. Start including uncertainty in your engineering analyses. And they pointed to several cases where we had had major setbacks in designs, which had happened because an analysis, a process, a design seemed to be good, and according to our measurements, it should have been good, but because we didn't understand how uncertain we were in our estimates, in our predictions, we made the wrong call. And that resulted in a lot of rework later. So the action item to answer this was given to the statistics group, particularly to its senior fellow, and over the next 3 years, there was a large internal R&D effort by that fellow and the rest of the statistics group to start learning more about how engineering models can take uncertainty into account, how our analyses can take that into account, and how we could improve the way we do engineering here. Now, at the end of those 3 years, they were ready to present it to the leadership, and leadership agreed to give a small amount of funding to start the Sensitivity and Uncertainty Analysis Special Initiative. It was just enough to get us off the ground with 2 or 3 pilot projects in some major areas of engineering, the ones most noted for having turnback problems, turbines, bearing systems, and fan blades. Just one project in each area. But we came back with some great success from those projects. And by 2008, leadership had agreed to give us full funding for a strategic initiative. We weren't good enough quite yet to be an actual group, a real discipline in engineering, but we were good enough to receive steady funding over the course of those years and create more and more DFV projects. Now, although it's not shown on the timeline here we stand at 2013, and as of January 1st this year, DFV is now a formal discipline at Pratt Whitney with its own full-time employees. And we're doing more and more projects all the time. In fact, our leadership's current idea of it is they want DFV to go viral. They're starting to use some common slang. They want to see it used everywhere in engineering, getting out into manufacturing, and even throughout the rest of UTC. They're that pleased with it. So in addition to this major drive that the UTC Technical Advisory Committee gave us, we were smart to keep in mind when we were doing those 3 years of internal research and development that that really isn't the only challenge Pratt & Whitney faces. And as we're developing our answer to that challenge, as we're creating our solution, we need to keep in mind the other challenges Pratt faces, and can we somehow answer those? Well, the first major challenge that our leadership had always proposed to us is the challenge to reduce design iterations. We form a design, we analyze it, it seems like it's good to go. But as soon as you put it out there in pre-production or in production, you start seeing supplier-to-supplier differences, batch-to-batch differences, part-to-part within a batch, and then, of course, the wear and tear of time. And suddenly, several years down the road, you realize that an uncomfortably large proportion of your population don't meet their requirements. And that means a lot of time and a lot of money in corrective action. If we could find some way to catch those problems very early on so that we didn't have to go back to the drawing board and redo a design, we stood to save a lot of time and a lot of money and really increase our reputation out there in the industry. Then there was the challenge to reduce cost. Of course, this is everybody's problem. But in specific, it occurred to us that a lot of decisions in Pratt & Whitney, they're made by careful analyses and computer models, but there are still some things, some ideas, which we base on our 100 years of experience in the industry. Things that we may never have, or if we have, we don't know, taken to the test bench and proven. Ideas about what really is important to a design and what isn't. We've never come through and challenged those. We've never really gathered the data, put it on a Pareto chart, and seen for ourselves what really are the drivers of a particular problem and what are not the drivers. Because if we're wasting money trying to control and analyze something that's not an important driver, that's an opportunity for us. And that's something statistics could help out with. Then there was the challenge to maximize stage life. Okay, this is a little specific to the aerospace industry, but it's analogous to what you can find elsewhere. We've got turbine blades spinning on a rotor inside of an engine. Anytime one of those blades fail out of wheels of 40, 50, 60 blades, the engine has to be removed from the aircraft it's installed in, almost completely disassembled. The rotor has to be taken out and completely replaced. All of those parts are limited to that lowest life, that weakest link. Think about the cost of the bills you get when your car comes back and they have engine trouble that needs to be worked on. Can you imagine how expensive those bills are when it's a jet engine that's got to get taken apart? We stood to save a lot of time and money if we could improve this weakest link phenomenon in the engine. And of course, engineers already understood that if they could just increase the median life, that could help solve the problem. But what we really needed them to understand is that wasn't the only way to solve it. If they could understand and then reduce their variation in lives, they could get just the same benefit, and usually with much less work. And the last challenge, increasing the speed of design studies and optimization. As computers become more and more powerful, we're trying to get things done faster and faster. But the same things that make us really good designers, having complicated models that very closely emulate the physics that take place out there in the real world, models that we've been working on for years, can be what works against us. Some of those models take days or even weeks to run through one single design. Is there something statistics can offer to help us shorten the time it takes to use a model? Maybe some kind of a shortcut around the model. That was another area that we could explore. So as I said, in 2006, we came forward with the idea of design for variation. This was proposed by Pratt & Whitney statistical fellow Grant Ryman as the idea to quantify and understand our risks of not meeting designs when we're making them. And once we can do that, we can work to control those risks up front before we discover a problem out in the field. Now obviously, out here in the industry, you don't have time to develop a whole new field of statistics. We didn't have to. We leveraged a lot of the work already being done in academia on just this kind of problem. Tony O'Hagan and his graduate students, including Mark Kennedy, the University of Sheffield in England, they had already published several papers and written their own software on how to do Bayesian model calibration and uncertainty quantification. Similarly, groups of researchers at Los Alamos National Labs had worked out their own software to perform similar calculations, and they'd written several papers on exactly how to apply those methods in the software to real-world industry-type problems and just what kind of success you could get out of it. So building on the work that they'd already done, we set up a framework for how these tools and methods could be used at Pratt & Whitney to augment our existing design processes. I'll summarize it for you here briefly, the DFV method. It starts by turning all of our engineering models into probabilistic models. They need to learn to speak in terms of probability distributions. We statisticians know that there's very few real-world situations where you have a 0 probability of exceeding your requirements and getting something to fail. The whole point is trying to get the probability of exceeding those requirements to be as small as possible. Once we get our models to start thinking in that way, we can really quantify, based on the percent of fallout, the percent of bad parts, what designs are better than what other designs. Once we accomplish that step, now we have to look at the engineering models themselves and how accurate are they and how long do they take to run. As I said, some of these are very old, and complex models like fluid dynamic models can take weeks to run. We could introduce statistical tools like emulators that would use the data from the original model and create a shortcut version. We could also use Bayesian calibration to calibrate those models to real-world data, making them more accurate. Then it would just be a matter of evaluating many designs, as many as we can, hundreds, thousands, and comparing where all of them stand against the requirements so that we can pick the best one. And it's not over there. As you all know, the most important part of all this is not just getting to the point where you have an idea what the answer is. You have to verify that answer. We needed to collect data from the labs, from the rigs, from the field that we could use to validate that the design we chose really was as good as our models expected it to be. And then statistical process control's got to come into play. It's got to help us keep true to that design in manufacturing as we move forward. The last step was writing standard work documents, documenting everything that we've done with the model to make it DFV-enabled, and what this new tool could be used for and how it could be used. Because we all won't be here forever. Eventually, we all hope to retire with nice pensions. Someone's going to have to pick up after we're gone. So now I'd like to spend some time talking about key elements of DFV that allowed us to succeed. When we first started this, we already had an idea of what we were going to need to really make this work, a short list. Well, that list quickly grew after we started really applying DFV out in engineering. And I'm going to go over some of those key elements now. The first is parametric modeling. Our existing engineering is what's shown on the top of this slide here. They take a single design, a single blue triangle. Sometimes they'd add margin into that single design to replicate what they thought was a worst case. But in the end, it was only one design. That design would be run through some kind of an engineering model, usually a computer code of some sort, and that model would predict how this design was going to perform. Maybe it was measuring stress, max temperature, life, durability. But either way, you'd get a single prediction out of that model, and it would either meet the customer's requirements or it wouldn't. Either you're back to the drawing board or you move forward with this one. We needed all engineering models to start working parametrically. They needed to take thousands of different designs, each one slightly different than the other due to manufacturing tolerances, due to wear over time, and run each and every one of those through the model. And then we also need to add in the uncertainty around the model itself, which we learn about when we calibrate it against field data, so that we get a full probability distribution of how these different parts are going to perform out in the field and how many of them are not going to meet our requirements. And since you're getting this massive data set of Monte Carlo runs, you might as well use it to perform a sensitivity analysis while you're at it, which is going to let you understand what's driving that output. Now you know what are the most important inputs into the model, and more importantly, you know what the least important are. Those are the ones that you should not waste too much time and effort trying to control going forward. Do you really need statistical process control on those, or can you lighten up? Next, let's talk a little bit about the tools and methods. Obviously, it wasn't enough to just tell the engineers, here's what's going to happen, and maybe here's how we're going to do it. They needed to be able to do it themselves. We had a statistics group of probably about 6 people, and that's for several hundred engineers. We couldn't do it all ourselves. We had to teach the engineers how to do it. And to do that, we needed to bring the higher level statistical tools to them in a way that they could use them. To start off, Gaussian process emulators. Remember I mentioned that a lot of these computer codes took days and weeks to run. They were simply impractical. Well, by using some kind of an emulator to simulate what the model's output would be for a given set of input data, We had a simple mathematical model that could return a prediction in a matter of seconds or, at worst case, minutes, as opposed to the days or weeks it would have taken otherwise. Gaussian process emulators specifically, which quantify uncertainty in between the training data points, have been incredibly useful to us. Essentially, we just explained it to the engineers as it's a fancy version of a response surface design. That's good enough for them. Then it's just a matter of getting them to take that long-running model through a series of training data sets so that they can hand us the training data input and output to create the emulator with. That's how we get down to the second tool, the Latin Hypercube experimental designs. That's our preferred method for how to collect the training data to make those emulators. We've already been teaching our engineers about basic factorial designs and response surface designs. Space-filling designs, like a Latin hypercube, are a completely different story, but they've taken to the idea well enough. We explained to them exactly what it is. It's a design of experiment that's meant to use many runs instead of very few, but with computer models, you should be able to afford to do that. You're not spending time creating a lab setup, and then collecting the data from that so that the emulator built on it doesn't have very far to interpolate between any two possible points. Then there's tool number 3, variance-based sensitivity analysis. Like I said, this is something we had the opportunity to create while we're running this Monte Carlo of all these designs. Now, our engineers already knew the idea of a sensitivity analysis, but they weren't usually doing it in a full method. They were doing part-by-part sensitivity analyses, just testing one thing at a time. They were not getting any understanding of interactions between inputs, and they weren't always getting a full sensitivity analysis of all the inputs that they really should be looking at in their models, just maybe what they felt were the top 3 or 4. Test those at a low or high level and see what comes out of it. In the best cases, they were running a factorial design and then analyzing the results there. But even then, they usually weren't covering all the inputs. We found that we could introduce them to how to do a full variance-based sensitivity analysis. Obviously, they weren't going to do it by hand. We were going to provide them with the software to do it. And we, in turn, got that from Los Alamos National Labs and from Mark Kennedy. The fourth tool we introduced them to was Kennedy and O'Hagan Bayesian model calibration, which, of course, Tony O'Hagan and Mark Kennedy talk about in detail in many of their papers. It's the Bayesian method for how to take those field data points or those rig test points or those lab data points that we can get them to collect, even though we only usually have just a few, we can't collect many, and compare them to the existing model. Then you quantify the bias, which usually isn't a constant value, it's a function over the design space between the real-world values in the model. Using that information, you can calibrate inputs the model has that we couldn't get in the real world and figure out what values they must have been to give us that kind of discrepancy. And then we can take account of any remaining uncertainty in the random error when we make predictions. As I said, we obviously weren't expecting our engineers to know and do this stuff on their own. We were providing them with software tools and the proper ways to use those tools. And then the STAT group, we're the ones that monitor how the tools are being used, are they of good enough quality, what improvements do we need to make, and where do we need to make them first. Okay, methods and processes. So we had tools. We had an idea of what to do. But we still need to make it very clear to the engineers. They've got enough to worry about. We don't need to make things confusing for them. We wanted to get momentum with this. We wanted everyone to agree it was all a good idea. So we tried to write something out, a process that they all could understand. It was going to be general enough that it would apply equally to every area of engineering, whether someone was designing bearings or designing turbine blades or analyzing data out of field engines. But it was also going to be defined well enough so that there really wouldn't be ambiguity about what we were asking them to do. It took a lot of iteration, but within a year or so, we got it nailed down to 10 steps. This is similar to how DMAIA guides the Six Sigma practice. And the idea, when we advertise this to them, is it's something you only have to do once. For any model, yes, this is going to be a bit of work, but if you go through it once, you have a tool you can use from here on out that's capable of doing so much more than your original was. a strategic plan. That was another thing that we definitely had to have. And this, it wasn't so much for our own success as it was for getting people behind us, especially management. They're not keen on wasting money, and they wanted us to prove to them that we weren't going to. So we took a look at all the different areas of engineering in the engine. We've got mechanical systems and externals. They're doing bearings and pipes along the outside of the engine. We've got combustor and augmenter that are designing the areas of the engine where fuel is burned. We've got turbine areas controlling the blades in the hottest area of the engine, fans and compressors, the blades at the front of the engine, and a number of other areas that are covering data that's collected or the integration of the engine with the aircraft, a lot of different groups. We had limited funding, and we wanted to make sure that everybody got the word out equally. So we picked one project in each area, one key project. We chose a model that was frequently used, and if possible, one that had caused us a lot of pain in the past, and made that our first go in that area of engineering. This way, everybody got to see something related to the area they worked in. And hopefully, because we were targeting the most important processes and the ones that caused the most pain, we would be showing them our best example of what DFV could do for them. We chose experts in the areas, in each of these areas, to lead those projects with us. Again, we know DFV, we know statistics, but we still need the engineers' help to actually do this. And using those leaders, we carried through a project in each of these areas. Now, unfortunately, I can't list all the details for you here, but I will tell you that what started as one project in each of these areas, the version today is going to show you about 12 or 13 different modeling processes in each of those areas that we have DFV-enabled. Related to that strategic vision, there needed to be a very clear value of this to the business if we were going to keep our funding and if we were going to keep the momentum going. So we had to be very upfront, presenting to our leadership, here is what DFV is going to do for you. Your challenges, you wanted us to reduce design iterations. Well, if we can put uncertainty modeling and model calibration in there for the engineers, we should be able to catch these possible setbacks up front, because we should be able to see that the design has a very high chance of not meeting its requirements. You want us to reduce cost? Let us do sensitivity analyses. Let us see where we've just been assuming we need to control features when it might turn out that modern-day designs don't really need control there. You want to maximize stage life. Let's use this DFV process on the rotor model. Let's understand all the variability and uncertainty in rotor life so that we can figure out what's going to buy us more. Decreasing the variation, increasing the average life, both, and how are we going to do it? And you wanted us to increase our speed in design studies and optimizations. Let us bring DFV across all of engineering when they're all using things like emulators and uncertainty calibration models. Things are going to work much faster. They can avoid some of those long-running old models. They can use some new IT tools. They're going to make things far quicker, and we'll see if we can't get things pulled down. The funding increased that we got as these benefits were realized from one project working to 3 to 5 to 10. We were taken more and more seriously around here, and that's how we slowly grew from being just a small special initiative to a strategic initiative, now to being our own discipline. And those pilot engineers, the first ones that really saw the potential DFV had to change the way engineering worked, they were the ones that became our advocates out there in the engineering. Of course, there was a lot of people that weren't too happy about the idea that we should change the whole way we do our modeling processes. You can't blame them. They're used to how they've done it, and mostly it's worked well in the past. And now we're talking about doing all of this work to change how these models work, to make them parametric, to collect data and calibrate them. Is it really worth it? The best way to answer that was to just find those few engineers in each area who really thought this was a good idea and we should give it a try, to have them lead the pilot projects for us and to let their enthusiasm and their success stories spread across the local engineers and management. That did a far better job of convincing them than anything we as the staff group could have said. Here's a good example of something that was not on our list for keys to success to begin with, but we really quickly learned just how important it was. High-performance computing. Now, as it turns out, Pratt Whitney actually already had a high-performance computing group when DFV first was in its infancy. But we didn't really realize that each other existed at first. It was more of a happy coincidence we found each other when we started working, and suddenly realized that we have this group of really intelligent individuals with some great tools out there that could help us make everything we wanted to do happen. The first thing they introduced us to was automated workflows in commercial softwares like iSight. These are designed to help third-party softwares and different file types all lead into one another and feed into one another automatically without having a person in the loop. This is something we end up doing frequently around here. When ANSYS models have to feed their results into an Excel spreadsheet that calculations are done in, and final results have to get tabulated, and some of those results then have to feed into a completely separate model that was written in Fortran. Softwares for automated workflows made all of that possible. And of course, if you're going to use a Monte Carlo approach and run thousands of designs through a model, you don't want to have a process that's got to have a person in the loop processing things manually for each and every one of those designs. In addition to the automated workflows, getting back to the idea that we needed to run thousands of designs through the model, well, if one model can run in an hour or two, and of course, if we're going to run thousands of designs through, that's going to stack up. The IT group gave us framework for parallel computing. They had already created batch rings of Linux or Windows computers. Any one computer on that ring, using a software called PCC, could take one large job that could be broken up into chunks. Each chunk was a Monte Carlo run. Each chunk was a separate design, and send those chunks out to every computer on the ring. It could be processed, sent back to the main computer. All the results were tabulated together, and then the final results handed back to the user. This is what changed DFV from being possible to practical. One case in point, we had a model that to run each different design one after another would have taken us 60 days. When we made it parallel, we got everything back in 2 days, and that includes the time it took to make all the pretty PowerPoint slides to show management. And the last one, communication and education. And I cannot underscore the importance of this enough. We couldn't just be statisticians. We couldn't just be good with numbers to make this happen. We had to be good speakers. We had to be good teachers, and we had to be good lobbyists. We instituted classroom training, teaching all of the engineers interested how to use the DFV tools, how to use the DFV process, how to overcome common challenges when doing one of these projects, to get the word out there. And it wasn't enough to train the engineers. We had to turn around and train the managers and the executives as well. They needed to understand, at least at a high level, what it was that we were doing. And they needed to understand how to judge or score DFV projects performed by their engineering teams so that they really could have confidence in the work their teams had done. We turned around and wrote standard work based on the classroom training so that what we know and what we learned should subsist through all successive generations of engineers. And we also took advantage of our company's wiki. Like the Wikipedia you're all familiar with, our own internal wiki let us very rapidly create and post information for people to use and edit if they so chose. We used it to post contact information, updates on the software because we're always upgrading it, and updates on projects happening in each of the different areas of engineering so that anyone interested can come in and learn what's already being done, particularly in their area if they're looking for someone to talk to. And of course, hours upon hours of presentations to leadership and engineers over the course of the past 6 years. From starting by trying to convince them that DFV was worth initial funding, to showing them our success, to convincing them they should give us more money, to showing more success, to convincing them that they should give us their own discipline, and now regular updates about how that discipline is performing. And of course, we couldn't have done it without the area experts, our mentors in each major area of engineering who saw the potential for this before anyone else, took a chance with us, and are now the leaders in their areas. So now that we've talked about the keys to success, I want to give you a close look at 2 specific success stories we have when we applied DFV here at Pratt Whitney. The first is on the topic of high cycle fatigue. Somewhat fancy name. Translation. Fatigue is just looking at when stress on a part, in this case a turbine blade spinning around in the hot part of the engine, exceeds the material strength of that blade. Simple enough. We call it high cycle fatigue, or HCF, and an HCF fractures what happens when you hit a stress that exceeds your strength. This is a very powerful failure mode. It can do a lot of damage. So, of course, every aerospace company out there does a lot of work to prevent these from ever happening. We create our designs first and foremost to prevent this. But it has happened in the past that our methods for evaluating and analyzing this have bitten us back. The industry, every aerospace company, the Air Force, the DoD, the entire industry has always analyzed HCF the same way. They'll plot out their material strength for the material given blades made out of. And then they'll take a small number of blades and actually test them against varying levels of strength. At the end, they'll record the highest level of stress seen on any one of those blades, just the maximum. Then they put a margin on the material strength line that they plotted, a legacy margin that was developed over time as, hey, this worked. And as long as that high stress that we observed didn't exceed that legacy margin, then we conclude that the design is good enough to proceed with the rest of design, testing, and pre-production. A whole lot more money and a whole lot more effort are spent testing it in the next round. And it has happened before that a blade design has looked good. It's come up just like that red point, well below the legacy margin. But then when we spend another few $1 million in another year or so and get back another round of blades, all of a sudden 20, 30, 40% of those blades fractured with HCF fractures. Back to the drawing board. It's a very painful experience, I can assure you. So we realized from the start, why are we just using the maximum? Why are we just using one data point and throwing out all the rest of the stress data we collected? Let's make a probabilistic version of an HCF model. Let's start looking at the entire distribution of stresses, try to predict how bad the future ones will get, and what the failure rate of blades will be when that stress that they see exceeds the material strength line. We proved that this could work as one of our first pilot projects to management by taking an old example where we had a blade go through one of these, it looks good, but then it fails situation. We ran it through our probabilistic model and showed them that if we had had that model back then, we would have predicted, despite the fact that the max stress you saw was low, 30% of your blades were actually going to exceed material strength. We could have avoided the whole thing if we'd had it back then. It was a pretty convincing argument, and that's how we took the project through to completion. Currently, we're using the same approach to validate all of our blade designs. The industry still uses the max stress, but we are also using the probabilistic model to reassure ourselves that the design is good. And someday, we expect that the entire industry will start looking at everything probabilistically from the beginning. The second story I want to share with you is also related to turbine blades, and this was also one of our earlier projects. But we're not talking about stress anymore. Now we're talking about airflow. Now, it may surprise you to know that those turbine blades that are spinning around in the hot part of the engine, right behind the compressor, right behind where the fuel is burned, those blades actually have a melting temperature that can be as much as 800 degrees below the temperature in that part of the engine. That fuel burns hot. So how do we even get jet engines to work if those blades are exceeding their melting temperature? Well, the key is blades aren't solid. They're actually partially hollow. Cold air from outside the engine flows through ducts and into the hollow center of the blade, then out through small passages and air holes that are dotting the surface of the blades. That cool air ends up forming a film over the blade that insulates it from the hot temperatures in that area of the engine and protects it. But given what I just said, you can probably understand how it's extremely important that we put those holes in the exact right place and we make them the right size so that that air skin is kept at proper thickness, proper temperature. If you have insufficient, even just over one small part of the blade, that part's going to start melting away. And guess what? The engine will probably still work, but this just means you're going to have to remove it from the aircraft when you find it, take it all apart, take the turbine out, put a new one in, and here comes your new repair bill. Best if we can avoid that. But this is a very complicated system. It's not just straight lines going out to the surface of the blade. It's a very complicated 3D process. In fact, making these blades takes months of repetitive steps, one after another, to get from a solid piece of metal to the semi-hollow one with holes in it. Now, of course, we would rather be safe than sorry. So we always suspected that the process we were using to test each blade we produced and say either it has enough airflow or it doesn't was probably conservative. But we knew that we were probably scrapping blades that really would have performed just fine. But we didn't know exactly how much. We never actually calibrated the testing we were using against real-world performance of the airfoils. So when this project began, the whole point was just to try to calibrate that model, to take it, to collect field data on the actual airflow around airfoils, and calibrate the existing model so it could be more accurate, and we wouldn't be scrapping quite as many blades. That worked, but in the process, we also found out we had another opportunity. Because we made the model parametric, able to take any possible set of inputs and not just the one set of nominal and design inputs that it was created with, we found that we could take any airfoil anywhere in the process of being produced and refined, take all of the inputs that are known, and just put distributions around the ones that haven't yet been created to reflect their specs, run it through in Monte Carlo, and now you get a distribution that shows you what your chances are of this blade, when it's finally finished being produced, meeting your airfoil requirements or not meeting them. That plot actually shown in the upper right-hand side is one example of a blade that would not be meeting its requirements, most likely. Most of the probability is in the blue. It'll probably be okay, but there's a sizable probability in the red with insufficient airflow. Of course, since they do this process in steps, producing the blades, it wouldn't be too hard to adjust the future steps that haven't been done yet to try to compensate for whatever was done early in the process, which is making it look like we might not pass this blade. And once the processes for that were developed and the airfoil team felt comfortable with what they were doing, they started cutting their scrap rate by as much as 80% based on not only knowing when an airfoil really was good or really wasn't good to proceed on, and also being able to adjust production as they went to make sure that any given airfoil has the maximum chance to produce good airflow. So there's two small examples among a very large community of engineers. Looking at things from a more general level, all of these DFV projects, which to date have only been on individual components, piece parts, have yielded an estimated 64 to 88% return on investment. From all the improvements we've made in optimization procedures, automating models, emulating things to save time, reducing the design iterations, and improving our ability to do a root cause investigation. We expect that to increase in the next few years, especially once they take these models they've made and just pull them out of the box for use on the next engine design, the next engine program. Then, we intend to start using design for variation now at a system level, since we've wet our teeth on everything else. If we start using it to predict our reliability goals, our performance metrics, we expect we could save as much as 40 times the amount we put into it, shortening our development programs and proving well ahead of letting the engines run out for thousands of hours that we will meet our metrics. So to wrap all this up, here's what we learned about statistical engineering and bringing it into industry from design for variation. Here's what we feel everyone would need to do to make this work. First off, you need some kind of a generalized structure. Think DMAIC. Think giving people some kind of a written standard. It doesn't have to be poetry. It doesn't have to be simple and easy to put in an acronym, but it has to be well enough defined that they know what you're talking about, but general enough that they don't think it can only be done in one or two places. Anyone could do it. And then start with a small, high-visibility problem to create your first success story with. It really helps if you can find someone out there who sees the potential for what this can do and is willing to work with you. Their expertise in engineering, your expertise in statistics. And marketing, above all, market what you create, both to practitioners and to leadership. Make sure that you share and quantify with them costs of challenges that SE can be applied to. How much is it costing you right now to correct problems manually? How much did the most recent setback in design cost you? If that had been prevented, maybe by using statistical engineering, think of what could have been saved. And what challenges might you face in the near future that statistical engineering could really help with, if only we had the opportunity to use it. And I strongly recommend gathering your methods and your tools together into a toolbox. We gave our engineers the DFV toolbox. It's just the collection of standard work documents and of software that we gave them to use. Something we have to keep monitoring and keep improving every chance we get, because trust me, they find new ways to use it every day. And keep in mind, there is no need to create these tools yourselves in all but the most special circumstances. There's already a lot of tools being created out there. There's universities and private groups that are still creating software to do sensitivity analyses and uncertainty analyses like we are doing. And there's got to be software out there to do any other type of statistical engineering that you decide to bring into your organization. You don't need to do all that background work yourself. You want to identify that expert, every major area, who can help you bring it out. We find sometimes, depending on the person we talk to, they know we're not an engineer. They know we don't have engineering training. And sometimes they're taking what we say with a grain of salt because they know that. So a big part of our success was getting the people who are engineers and who think and speak engineering to speak for us and to really convince their coworkers that this could work and this could be something worth the effort. And last but not least, make sure that you bring all of this into your company's training curriculum, even if it's just a one-time thing. This is all about teaching the people in your organization how thinking about things from a statistical point of view or using more powerful statistical tools than just confidence intervals or simple regression models could solve a lot of your really big problems. Train them to believe that it is worth the effort. Okay, and one last thing I'd just like to share with you. Obviously, we had to keep things at a high level today, but if you'd be interested in learning more about the DFV process we created and what we did for it, this presentation was all based on an article that we published in the Quality Engineering Journal in March of 2012. It's a much longer read. In fact, the first version was 60 pages. We did bring it down after that, but it's worth the read with more detail. And of course, we always appreciate anyone who'd like to contact us and ask questions. We'd love to spread around the success. All right, so that's it. Thank you all for being a fantastic audience. Joel?
All right, thank you, Jamie. That was excellent, and we did have a few questions come up here, so I'll go ahead and answer one that just popped up quickly, and that is whether or not this is recorded. We are being recorded at the moment, and that will be posted to the ASQ Stat Division's YouTube channel, hopefully here in about an hour or so after the webinar. Everyone will receive a follow-up email who attended, and that will provide a link to the Stat Division channel. Otherwise, Jamie, do you want me to ask you the questions, or would you like to read through? Or?
Well, I'll ask you, Joel, to help me out here since I'm still trying to figure out the the interface on the side of the screen.
I am too, but I might be slightly ahead based on experience. So one question was whether or not all the software used in Pratt Whitney's development was created in-house, or are there off-the-shelf packages that can be used? And I obviously touched on that some here at the end, but are you using off-the-shelf packages in-house, or is everything what was developed there?
So unfortunately, we didn't find a lot in the commonly available software. There wasn't a lot at that point in SAS or JMP or Minitab, and there still isn't much that we could use. We did find those softwares that were developed by Los Alamos and developed by Mark Kennedy and started to use those. But of course, we did do a lot of improvements on them in-house. A lot of them were refinements to usability to make things more logical for the engineers to interact with, and some of them were actually increasing the capability of the software itself. But that had been kept to more or less a minimum. The majority of the work to create those softwares, to really do the analysis, that had already been done for us, and that was the best part.
Okay. And have you heard of this approach being implemented in the electric utility industry, or I guess a similar industry, or do you have any references to that?
So none that I know of, although I will say that there are other industries like GE. In fact, the original paper I talked about on statistical engineering, Roger Hurl, is from GE. They are familiar with some of the details of the approach that we use, and they do some similar things on their end. I would like to see this start being used in those industries more.
Excellent. Yep. And another one, obviously this wasn't part of the presentation, but someone did ask if you have a complete example of a design for variation application from the beginning to very end, including any conclusions, or I don't know if that's something that you just weren't able to share, or if it's just too in-depth to share.
Well, there's more detail in the Design for Variation paper we wrote. We were able to be a little more long-winded there. And that's probably about as detailed as we were able to get. Of course, we have to balance that constant demand between wanting to share what we did and having to balance the whole proprietary information and sensitive Defense Department information.
Sure, and I believe all ASQ members can get to the article through the ASQ website if you're logged in, if it was in quality engineering. So, do you have, or does Pratt Whitney have like certified subject matter experts on statistical engineering, kind of like you have master black belts in the Lean Six Sigma world?
That's something we're still working toward. Of course, we did just become a discipline. So now I am the recognized discipline chief, and Grant Ryman is the recognized senior fellow for DFV. We're still developing toward that, but it's actually quite funny that, of course, we started all this long before Hurl's paper came out, and when it did, we all looked at it and went, oh, yeah, that works, and we know because we've actually done that. We just didn't know it was called statistical engineering.
Excellent. And do you know if this can be combined with lean product design processes?
Yes, and that's part of what let us succeed in trying this out to begin with, because lean was teaching us that you needed to reduce your effort in the short term, in the long term, by tackling things earlier on. So one necessary class that all people related to DFV and all engineers who are trying to increase their quality proficiencies take are the lean courses.
Excellent. And where did you get the material strength probability distributions that you showed?
I'm afraid those are a little bit more cartoons created just to keep things accessible for this example.
Okay.
But it doesn't look too different in idea than what are really used. In fact, I found a few Department of Defense papers when I Googled it that actually explain what's called the Goodman method in more detail and show you what that really looks like.
Okay, excellent. Last question, unless anything else comes up here. How does design for variation relate to robust design?
You know, it's just another name for the same type of thing. It's about looking for the best design possible that's not only going to perform well on average, but perform well at both sides of the probability distribution.
Okay, and we did have one more come up here. How did you establish the probabilistic requirements?
And that is a really good question. So we actually have a whole standard work written on that. In some cases, that's pretty easy because the government or the airframer will just hand us down a requirement. We want you to meet this specific requirement. Though we have had to go back to them and say, all right, but when we turn this into a distribution, you have to tell us what tiny % of the time you're willing to let us exceed that requirement and still call this a good design. It may be 0.1%, it may be 0.001%. That's required some conversations with some of our customers. I think we found that the military has been very supportive of this idea moving forward, and they actually have started putting their requirements in these probabilistic terms. You will not exceed this any more than this often. But in the commercial world, we're still getting there. They will give us requirements, but we have to work with them to make those requirements probabilistic. In the meantime, Six Sigma is a good requirement to apply to any number they give us.
Excellent. Okay, well, that's the end of our questions. To reiterate for everyone, you will receive a follow-up email. We'll have a link to the YouTube channel where the recording will be posted. sure how quickly that email is going to go out, so it may beat me to having the video uploaded, but hopefully not. You'll be able to view that. Other past webinars are also on the channel as well. That will also come from an email address. If any further questions come up, feel free to respond to that. And I will either answer questions or get them to Jaime, and she can answer them. So, Jaime, thank you again for presenting today. It was a very popular webinar based on live attendees, and hopefully everyone got a lot out of it, and we'll continue to from viewing recording after the fact. So thanks again, and everybody please stay tuned for our next webinar.
And thank you all.